So today we're looking at calculating an enthalpy of combustion using calorimetry. So basically from an experiment where we burn a fuel and heat up some water, and from the temperature rise of the water we can calculate the energy given out and therefore the enthalpy change. So the equation we use for this is Q equals mc delta T. And M will stand for mass, C for specific heat capacity, and delta T, the change in temperature, and it's worthwhile looking at the units for these because our specific heat capacity is given in joules per gram per Kelvin, and our mass is grams, and our change in temperature is Kelvin. Even if it's given in degrees C, our change in temperature will still be Kelvin. So change is the same even though the actual values aren't the same. And if we times them all together, we'll see that grams times joules per gram per Kelvin times Kelvin will end up in a unit of joules. So when we put our grams in here, specific heat capacity and temperature change, the answer will be given in joules, not kilojoules, which was what we want for an enthalpy change. The other thing we have to be careful of is the mass. So in the question here, a lot of students will put in the mass of 1.56 grams because that's the mass given in the question. But what we're interested in is the mass of water because that's what we're heating up from the combustion of the fuel, and that's what's telling us the energy that's being given out. And water is 1 gram per centimeter cubed, so we want this volume to be in centimeters cubed. And as 1 decimeter cubed is 1,000 centimeter cubed, then our water is 250 centimeters cubed, and therefore that will equal 250 grams. So now we can put that in our equation. So Q will equal 250 times the specific heat capacity of water, which is 4.18, times the temperature change of the water, which from 292.1 to 339.4 looks to me 47.3. And then if we times that together, we get 49,428.5 joules. But we've been asked to calculate not the energy given out, the enthalpy of combustion. And we know enthalpy change is kilojoules per mole. So our enthalpy change can be written as minus Q, but in kilojoules, divided by the number of moles. And I actually just remember this as minus the kilojoules over the moles. And so our energy in kilojoules, so if we divide Q by 1,000, we get 49.4285. And the number of moles, this is where our mass of propanol but the fuel we're burning will come in, because moles is mass over mR, which is 1.56 divided by the mR of propan 10, which would be 15 plus 14 plus 14 plus 17, 60. And then if we put that in our calculator, 49.4285 divided by 1.56 divided by 60 is 1901.096, which to three significant figures, 1,900 kilojoules per mole. And that's the enthalpy of combustion of propan 10.
Great. So presumably they will have done.
And just one thing, can you spot anything I've missed there, Atul?
Change in temperature, joules. Is there a unit?
It's not anything to do with units or calculation, really.
So you've got the mass of the water, that's correct. Specific heat capacity of the water. Change in temperature gives you the energy. Convert that to kilojoules, divide by the number of moles. Anything I can think of is an assumption that there's no heat loss.
Not an assumption, it's a sign. It's delta H is minus Q over N.
Yeah.
Because we've had a temperature rise, so it should be an exothermic reaction. And so I haven't carried on the minus sign here. So our enthalpy change is minus 1,900 kilojoules per mole. And I've just made a common mistake that students make, which is making sure the sign's correct.
Yeah.
For the answer.
Yeah, it's an exothermic reaction because the temperature goes up, so that's a useful check. And exothermic reactions have a negative energy. I was just in my physics brain there, because that's the physics equation, isn't it? Q equals C delta.
Yes, the Q doesn't come out as negative, because that's the actual energy given out. Yeah,
of course. And
the delta H, the enthalpy change does.